So today we are going to be talking about compactness, which is our first important property that a topological space can have. So the first thing we have to define, so our definition is going to be an open cover of a subset, a subset of X, which, by the way, is going to be our topological space. So let's say it has topology T, is a family sub alpha of open sets such that S is contained in the union of this family. Right. The next definition is going to be of compactness. So we say that the subset S is compact if for every open cover of S, there exists a finite subcover and that is a finite collection of open sets which belongs to this family and which still covers all of S, right? So S is contained in this in the union of these finitely many open sets. So as a first example, any finite set is compact. So consider, I can just label the points P1 through Pn. So let's consider this to be our set, and let U sub alpha, or alpha and A, be any open cover. So what this means is that if S is contained in the union of all the U sub alphas, that means for each I equal 1 through n, P sub I is contained in some U sub alpha sub I, right? Because if P sub I has to be contained in the union, which means it's contained in at least one of the U sub alphas for some alpha sub I in A. And we're denoting it alpha sub I in correspondence to the I of the point, right? So P1 is going to be contained in some U sub alpha, and we call that alpha alpha 1, for example. And thus, the sets U sub alpha 1 through U sub alpha n are a finite subcover. because essentially the process here is that we are picking one open set for each point in S. Clearly we can't do this in general. If S is an infinite set, we can't obtain a finite subcover by this process. But this is an example where we have an easy method to construct our finite subcover. Now we are going to consider some equivalent characterizations of compactness. So first, again, we're going to define another type of property. So let A sub alpha A be a family of sets. These are just any sets, not necessarily anything to do with topology. This family, we're going to say it has the finite intersection property. Intersection property if for each finite subset M of our index set A, right, the intersection over these finitely many sets in this family is always non-empty, right? So it's saying if I have this family has the finite intersection property if I can pick any finitely many of these sets, and I will always have a non-empty intersection. Now, we can use this for our new formulation. So alternate formulation of compactness. X is compact if and only if for every family of closed sets with the, or I should say, I should get rid of the for. X is compact if and only if every family of closed sets with the finite intersection property has a non-empty intersection, right? So notice that the finite intersection property does not guarantee this, right? Because it's only saying what happens when we take intersections of finitely many sets, right? This is saying what happens when we take the intersection of every set in the family. In many cases, that would be empty, but compactness guarantees that if the family consists of closed sets and it has the finite intersection property, then we are going to obtain a non-empty intersection. And so this is an important theorem that you should prove, right? So for this, and I don't know if I've mentioned this before, but for an if and only if type proof, you have to do two directions, right? First, you assume X is compact, and then you have to show that if I would just say, okay, X is compact let this be a family of closed sets with finite intersection property, and then I have to argue that this has a non-empty intersection. And then I have to go in the other direction. I have to start with a topological space such that every finite family of closed sets with the finite intersection property has a non-empty intersection, and then I would show that that is compact. I would do that by considering an open covering and then using this property to construct a finite subcover. We can also use this formulation to prove a closely sort of related result. So let X be compact. Let V sub I, where I in the natural numbers, be non-empty closed sets with V1 containing V2, which contains V3, which contains, and so on, right? So we have this sort of tower of sets. Then the intersection of all these sets is non-empty. And this is just a direct application of the alternate characterization of compactness, because this is a family of closed sets with the finite. You can show that this is a family of closed sets with the finite intersection property. And why is that? Because an intersection of finitely many of these V sub I is just going to be V sub I for the biggest I in that finite set, in that finite index set, right? Because you have this chain inclusion, so if you take an intersection, the intersection is just going to be the smallest set, right? And that's always going to be non-empty. So this has the finite intersection property, and therefore, since X is compact, the entire intersection is going to be non-empty. The last few things to note, if A is compact, B is closed, and B is a subset of A, then B is compact. So a closed subset of a compact space is, or a compact set is compact. And the proof of this goes like, well, first you want to prove that B is compact. So you would start with an open cover of B. But since what should I say? Since B is closed. Oh, and by the way, we are assuming here the topology is coming from X. So A, I guess I should write B is contained in A, which is contained in X, and our topology is coming from X. So B is closed, so X minus B is open. Although really, if you were dealing with the case where you're dealing with a subspace topology, then you could say, okay, like if you weren't, like technically you don't have to refer to X, you could refer to A if you're saying B is closed in A, right? It really just depends whether you're saying it's closed in A or whether it's closed in X. So Sweston, in this text that we're using, since my teacher never introduced the subspace topology we're always assuming that we're working with the topology on X. But in other texts, you would use the subspace topology that we introduced last time, and we would say A, we wouldn't have to make reference to this X. So really it just depends on the approach here, but I'm going to stick to the one that's in our notes. So X minus B is open, thus use of alpha union X minus B is an open cover of A. And once we have an open cover of A, this means there is a finite subcover of A. And since B is contained in A, this is necessarily a finite subcover of B, except you have to deal with sort of this extra set here, because you're looking for a finite subcover of this original collection. But clearly B is never going to be contained in X minus B, so you can just disregard it. So this gives a finite subcover of B. So thus B is compact. And the final thing, which I mentioned when we were talking about continuous functions, is that if f is a function from x to y, and this is a continuous function, and A is a compact subset of X, then f of A is compact in Y, right? And so for a short reasoning of this, again, you want to prove that this f of A is compact. So I'm going to use V sub alpha since we're working with the topology on Y. So let V sub alpha be open cover of f of A. And then I believe all you have to do is argue that the collection of f inverse of V sub alpha is an open cover of A. Of course, since f is continuous, we know that each of these is going to be open. So open because f is continuous. And then, so then there's a finite subcover which means that the V1 through Vn covers f of A. And so of course I'm skipping steps here, but I'm fairly certain that this is the general approach to the proof. Of course you should fill in the details. And so that's it for this lecture. Do you have any questions?
No, sir, I'm clear. It's understand.
All right, no, that's it.